Have you seen these filmed on iPhone commercials? I watched a YouTube video last week about the behind the scenes of actually how they film these. And it's just a regular production setup, dog. They have the huge professional lights. They have the audio equipment on these external booms.
I mean, it's absolutely cheating.
Yes, if you spend 50 grand on your set, you too can make a home movie that looks exactly like a
Maybe
studio.
we should just be walking around with a whole like lighting team and an audio team just tailing us. You know what I mean?
Filming our life. A full documentary film crew.
Yeah, exactly. Maybe what we need is a documentary of the making of Pre-Trained.
Begin to show, speaking patterns break the code. Pre-trained pod.
And welcome back to the Pre-Trained Pod. I'm Pierce.
And I'm Rich.
Richard, you seem
do I look different?
You look a little different. Pierce?
A little different, right?
A little different. What's going on with your camera?
I just got a new Mac. The new Macs come with this camera that you can like extend. You know what I mean? No, I'm just playing. I got an actual camera, dude. I kept seeing your video and I was like, damn, Pierce can't just be, looking this fresh. I gotta upgrade. So here we are.
You look fantastic. You look fantastic,
I appreciate it, man.
And this is probably a good PSA because what the heck am I talking about? This is an audio podcast. Turns out we have a video feed too. It's on YouTube.
Turns out. Who knew? I didn't know.
What an organic segue, Richard. Thank you so much.
Incredible.
Richard's got a plant in his background. He's on the top floor of his penthouse in London. He looks fantastic.
That's right. Dude, we're living the good life out here.
He looks fantastic. Check it out. Richard, I wasn't aware that it was apple season in the UK.
It's not just apple season, it's apple picking season, baby.
So you're picking some apples this weekend.
We're picking some apples, yeah. So we went apple picking on Sunday. And honestly, this is one of these things that I did growing up. And then for whatever reason, my family stopped when I was like 8. And then last year, I had this like neuron that kept firing that was telling me you should go apple picking. And I was like, okay, fine, let's do this. So we went apple picking last year. It was honestly the funnest thing I've done in years. And then we made a little apple pie.
Oh my God.
Little tradition. Yeah. It's cute.
How fun really is that? That's very autumnal. I feel like that's a very good symbolism for the seasons changing. Apple pie. Damn.
Yeah.
I get some of that.
Apple pie is weirdly delicious, dude. It was a very wholesome weekend.
Well, that's not so weird. Yeah, that's true. You're really getting back to your New England roots.
That's adorable. Right, dude.
Richard, that's actually a great segue because we have some news about apples this week as well. Although of the consumer varietal instead of the apple picking varietal.
How was that? You just did that transition. That was a great transition, dude. I had no idea we were going to go with that. Incredible.
Nor did I. That was straight off the dome.
He does it again, folks.
How does he pull it off?
So what's going on with Apple?
So Apple released a new model for protein folding, which is a little outside their area of traditional expertise, machine learning research, but we're going to talk about that. I think it's pretty interesting. We're also going to talk about OpenAI and NVIDIA's new 10 gigawatt data center partnership. There's a new eval data set, also from that same Frontier lab, and a new robotics model from Gemini.
Ooh.
You want to get into it?
Let's do it.
Okay, Richard. So OpenAI and NVIDIA's 10 gigawatt partnership. This is a pretty bonkers announcement. It broke this past week via joint press release from both of the companies. So they're trying to spin up 10 gigawatts of data center capacity just dedicated to GPUs, ostensibly from NVIDIA, considering the announcement is both of them. This involves this investment that NVIDIA is also making in OpenAI. So it makes sense that as one of their frontier partners, they would want to establish these data centers and only pull from GPUs that NVIDIA itself produces. The information broke a story today that extended this piece and said that Sam Altman's actually trying to spin up 250 gigawatts of data center capacity. And these would be net new data centers, right? Like they're not trying to co-opt existing data centers for GPUs. So this further extends the huge build out that we're seeing across the US, but also across some parts of Europe and the Gulf, where it's just a ton more data centers than frankly I ever imagined we would be seeing in 2025, considering how well established the internet already was. I feel like it's pretty easy to get lost in the sauce here. Like you're throwing out a ton of different numbers. Some people talking megawatts, some people talking gigawatts. Can you help break down exactly what this quantity of gigawatts means for the average consumer, or like in terms of data center capacity that they're trying to bring online here?
Oh, I'm so happy you asked. I actually had to explain the other day to someone what a watt was. And I realized I had no idea. So I had to do a little deep dive the other day to like really understand what a watt of energy is. And
This is
so
like physics curriculum.
it's one of these things that like you think you know, and then you start explaining it to someone and you're like, wait, I actually have no idea how this thing works. And then you feel embarrassed and then you just try to leave the conversation.
Yeah, then you choke, and then
That's right. That's right. So, okay, what is a watt? Okay, so 1 watt turns out is about the same amount of energy it would take to lift a small apple, speaking of apples, 1 meter in 1 second. So, watt is a time relative, I guess, unit of measurement. Okay, so it's basically energy over time. And so, 1 watt, as said, is an apple that you lift 1 meter in 1 second. So if you think about it, 700 watts, and I'll get to why I'm saying 700 in a second, but 700 watts is like lifting a barbell with 45-pound plates or 20-kilogram plates if you're in Europe on each side, deadlifting that 1 meter every second. Okay. So that's 700 watts is doing that continuously every second into perpetuity. Then you'd be putting out 700 watts of energy if you were doing that, like deadlifts every second.
and I should also add, as someone who is not a weightlifter, unlike Richard, that's actually quite a bit of weight. I mean,
Oh, yeah. So basically, that is for a lot of people a working set of weight. That's a lot of weight. Like this is actually like relatively heavy. Right? Like this would hurt your back if you haven't weightlifted before. This is like imagine 3 suitcases that you check into a plane stacked on top of each other, deadlifting them off the ground.
Yeah.
Okay.
Yeah.
And you have to do that every second. So you don't get any break. You keep doing this every second. You lift that up 1 meter, drop it down, lift it up, drop it down. That is what it would take to output 700 watts of energy. And so why am I saying 700 watts? 700 watts is the amount of energy that one of these new H200 NVIDIA chips requires at peak power usage. So in order to power one of these NVIDIA chips, effectively, the amount of power that you have to put in is the power that it would take to deadlift 70 kilograms, these 3 suitcases, over and over and over again into perpetuity. And here's the kicker. Models nowadays aren't just trained on one NVIDIA chip. They're trained on 10,000 or even 100,000 these days. So basically, think about it this way. In order to train a model that requires 100,000 NVIDIA GPUs, the amount of power required is like getting 100,000 people together in a room and them all deadlifting a barbell with, 1 plate on each side, 1 second for like weeks on end without breaks. No time to go to the bathroom, no time to eat.
Absolutely not.
Definitely no time to sleep.
No water.
100,000 people doing that for weeks on end. That's the amount of power we're talking about here. Okay.
Which is like 2 football stadiums filled with people just deadlifting 24/7.
I mean, it's apocalyptic, dude, right? Imagine just the mental image of this is just so disturbing to me. Imagine walking into a room and there's 100,000 people just deadlifting. But it's like the amount of energy required is just like crazy. And we're so far removed from the energy production because all of it is being produced, obviously, these days in a nuclear factory or a coal plant or, an energy windmill farm somewhere far away from us. We don't really understand what it requires to produce this much energy. How to produce energy just feels so far removed from our day-to-day lives. But anyway, so when we say that NVIDIA wants to produce a 10 gigawatt factory, so 10 gigawatts is 10 billion watts. That can power, in theory, somewhere on the order of 10 million GPUs. Okay. So, in other words, they're building this factory that is basically like having 10 million deadlifters doing deadlifting exercises in a room continuously. That is the amount of power that they're basically proposing to build in this data center. I find that's insane if you put it in those numbers.
Totally. I mean, one other benchmark, if we're drawing parallels to weightlifters, I don't know how many this is in terms of people lifting weights themselves, but the full quantity, that 250 gigawatts of energy capacity, is a third of the peak US power consumption that you see on a yearly basis. So when we think of like the overall power generation capacity that comes online, people talk about it as a spiky market or like a spiky industry because you don't need power at all times. It's why power bills usually will discount energy before 4 or 5 p.m. And then when people all go from their offices back home, air conditioners come online, lights come online, ovens come online. I guess many people don't have electric ovens, but whatever you need to actually live your lives. And instead of being in one centralized location like an office where you have economies of scale on electricity because you have one centralized AC unit or whatnot, you then have dispersed people and nighttime. So you have a lot more energy consumption. Then people go to bed and it draws down. So usually power plants or utilities will think of this as what is the peak amount of energy. And that's like right around 4 to 5 p.m.
Oh, it's like rush hour. Everyone's coming home from work.
Exactly.
Gotcha.
Exactly.
Yeah.
And some seasons are worse than others. Like usually in the peak summer, the peak is higher because a lot more people have air conditioning running than in the dead of winter where it's mostly heating. But mostly heating in the US at least is gas powered instead of electricity. So peak capacity, a third of all US power consumption just being dedicated to GPUs, which obviously means that the existing grid can't accommodate that. The existing grid, incidentally, I was talking to a friend about this weekend who knows a lot about the power space. It's a very interesting industry because you need to load balance in real time across the entire grid, or else there are drastic ramifications where your entire grid can potentially go down. So like every megawatt that you're pulling from the grid at one time has to be backed up by 1 megawatt of produced capacity in that time period. And you could obviously say like there are some batteries and there are, molten salt where you can store excess energy that then you could push back in the grid. And all that is true, but that's mostly under this bucket of this bridging layer of basically trying to temporarily bridge capacity. And power watt operators think of that usually order of sub like 30 minutes. Like if there's some unexpected spikes.
Okay.
It's usually those things are intended to be able to get you to ramp up power capacity within 30 minutes or maybe sub an hour. But it's that kind of order of magnitude of time. These are not like long tail or long time horizon energy storage mediums that are intended to float the grid.
So basically, everything we're using now is being produced in real time somewhere.
Yes, exactly right.
Wow.
Which basically means that in these bidding markets, what you're trying to do is just when you have peaking demand and you need to be able to meet that with peaking supply, you then have power generator operators spin up additional capacity in order to power that additional surplus. So you don't have to float the capacity via these like temporary bridge
That's
factors.
insane. I had no idea.
Yeah.
So what this means is if they're building out a factory that requires 250 gigawatts of energy at peak usage, someone is going to have to know how to produce 250 gigawatts of energy that currently we're not using. This has to come from somewhere.
Totally.
Wow.
So they're going to have to spin up, I would say, almost this entire 250 gigawatts. That's obviously a stretch goal, right? So maybe taking a little bit more concretely, the 10 gigawatts that they're saying as part of this announcement, they're going to need to find 10 gigawatts of energy somewhere from some supplier, which is then going to mean that they're going to have to bring more generation plants online because even in reserve, these plants aren't running at full capacity all the time. You could, in theory, use existing generation capacity and just say, hey, run your generation capacity at 100% utilization 100% of the time. You could definitely do that. I think that would probably unlock an order of 1 or 2 gigawatts across the entire country.
But we're hosed.
Yeah. Well, so
we really had to figure out how to produce more energy, like stat.
It means that we very much have to build new generation plants, which gets you into a lot of, I think, what people were talking about more with the whole like Build Back Better plan of permitting reform and the ability to accelerate our ability to both finance, but I think more to like permit new generation plants and facilities, because the way that things work right now, you need something like a 10-year lead time to build some of these plants. And if, generation capacity is increasing at a pretty linear rate, which it has historically, you can do a pretty good job of predicting that, of building towards it, of forecasting. But as we're seeing, at least now, non-linear and maybe even quadratic power increase, we're going to have to do something seriously different to build out just the electricity, not to mention the chips themselves, which I feel like is what people usually talk about. How is TSMC going to manufacture these many chips? That's definitely true. But I think at this point, it may be part of the framing of them putting in terms of gigawatts instead of just, the quantity of GPUs is to say, we're really looking down the pipe and thinking that we're going to need some pretty serious changes to the grid in order to accommodate this kind of load.
Wow. That's both fascinating and terrifying at the same time. Here's another point that I was thinking about as you were speaking. It feels like to me, the internet, as it's scaled and grown, no one has really thought about, oh, how are we going to have the capacity for the internet to grow at this rate? Like, I've never heard someone say, oh my God, more people are using Google now. So we're going to have to build all these energy factories. I don't think anyone's ever said that before, or at least it's not really part of public discourse. But it feels to me that fundamentally, this technology, chat, Claude, all of these tools, are such a drain on our existing infrastructure that we literally can't support their scaling. And it's just fascinating to me that for a lot of people, I think the internet and these tools, these AI tools, go in tandem. Like they feel very much like the same thing. But fundamentally, categorically, they're not. The internet can scale under, our existing infrastructure, whereas these new tools will literally require us building and maybe innovating new ways of generating electricity. I find that so fascinating.
Yeah, yeah. We really didn't have to consider it in the same kind of way. I imagine some of that is because personal computers put power pressure more on the consumer in like a distributed way, right? Like even if you have a really power hungry computer, I mean, by relative standards, it still draws far less than like a refrigerator. But
Yeah.
still, all of the computing that you did locally for a really long time was just local. And because of that, I think you could factor that in to regular power demand in a way that was a little bit easier to do. You basically just say, consumers and like office complex are going to draw this much more electricity because they have some of these on-prem servers or because they have, desktop computers and whatnot. It's on a much more of a local municipality basis. I think one of the big changes in data centers too, whether traditional cloud or with GPUs, is that it's just drawing from one municipality, right? Like by
Right.
definition, these things have to be in the same space. You can't have the interconnect nearly fast enough if you put them in a distributed fashion, especially for GPUs. So I think you also have much different considerations where you're saying this one region of Arizona or like Texas, for example, let's say that they have really low tax bases or they have some like government incentives to build data centers there. A lot of people are going to flock to that area. That means that that one point region in space is going to need to spin up the capacity to only power that one data center that might not also be in the global planning sense a particularly easy place to get energy to or like to build out the infrastructure to bring people to help develop that capacity because you're just going to go to wherever some combination of the electricity is the cheapest and some combination of wherever you can create data centers or build them in a tax efficient way.
The political interest too, right? There has to be a real push by legislators and politicians to invite these sorts of massive infrastructure projects into their own localities. This is a big ask fundamentally of any region to accommodate this sort of infrastructure. And it's really only places, as you were saying, I guess Arizona, Nevada, I guess Louisiana's building one too, maybe, that maybe have existing infrastructures to support this. Something that I find fascinating is the fact that fundamentally we're talking here about compute and optimal placement of these different nodes in this global network. But they operate under this constraint of local politics that factor in where they should place these optimal compute nodes, right? It's not optimal in a sense of computationally or cost effectiveness. It's optimal in the sense of where is it easiest to sort of sway political interest to actually enable this sort of a project to be established. I think that's so interesting.
Yeah, I do too. And the nexus of the different concerns as well, right? Where it's on one hand, you need to get this capacity online. On the other hand, I think companies are trying to minimize their overall tax burden. So that factors into
Yeah,
things as well. You need to be able to get the labor that's going to staff these plants, right? Like if
right.
you really, really put them in the middle of nowhere, you're going to have to either pay people more as like data center technicians to act on site, or you're going to need to figure out some other location for them to be because you need the talent. And then you also have the company considerations where most of them at this point have pledged to have some proportion or their whole proportion of compute to be carbon neutral. So you either need to like buy credits if you're pulling from sources that are otherwise non-carbon neutral, or you need to then find electricity sources that are themselves carbon neutral so they can factor into your overall electricity pledges. I'll tell you, I don't think most of the big companies, when they signed a lot of these pledges, were really expecting us to have this data center build out that we have already had. And I imagine that there's sub teams that are focused on like power sourcing and the actual enforcement of these different carbon neutral guarantees are really sweating right now to figure out how they're going to be
Oh
able to do
yeah.
this at
Oh
scale in order
yeah.
to meet what the consumer and the other infrastructure build out teams are saying is this is a business critical thing for us to do to build these more data centers.
Yeah, I mean, imagine getting a call from your boss and being like, "Hey, we're gonna have to build a data center that requires about a third of the peak power usage of the entire
Of the country.
continental
The
US.
country.
Yeah, good luck."
He's like, Chief, I was expecting this call. Here's my PowerPoint. I
It's
have you covered.
crazy.
It
Yeah.
is. It really is. Okay, Richard. Well, staying on this OpenAI beat, OpenAI this last week dropped this GDPVal benchmark data set. I feel like their metrics team within OpenAI has been really cooking lately. They've dropped, I think, 5 to 10 benchmark tasks just within the last year. And this has been a historical issue for a lot of the things that we end up using these models for right now. You've talked, I know, on a previous pod about the difficulties of benchmarking in the abstract. I think we're very much seeing that now, where each new generation of models will have, some golden task definition that they're really trying to strive for. And as we've increased in scaled compute, maybe up to these many hundreds of gigawatts worth of training capacity, they're getting better at these tasks. We then benchmark them on these tasks. And then they either have solved the task or gone 85% done, at which point that task almost loses its predictive or modeling power to be able to evaluate models. Because once
Yep,
some task is
exactly.
solved, we think, okay,
What's the
what else
point?
do we
We're
do?
like, it's done. Yeah,
What's the
exactly.
play?
Yeah.
We need to benchmark ourselves on something new. So you see this evolution of the models, but also this evolution of the benchmarks where they become much more difficult. And I think, interestingly, specifically for this new eval set, a lot more real world, a lot more practical of the task definitions. So what they ended up doing here was they got a bunch of professionals together and said, hey, you're an architect. Come up with a task definition that you would give some new employee that you've hired to your company. And we're going to benchmark GPT-5, but also the Claude and Gemini models against this task definition to see how well they do. And then the output of that would be scored with some combination of that same group of human experts and an AI model that itself is calibrated to be able to try to weigh in, validate this task. So it's a data set that's a combination of a lot of those different things across different professions. I'm wondering if you saw this data set drop and what you think of this overall evolution of this eval methodology that's trying to focus on more practical things in the wild.
Yeah, no, I did see this. I mean, this made a huge splash on Twitter. It feels like everyone and their moms was talking about this.
Especially the
I think that
moms. My mom was
especially the
talking
moms.
about it.
Yeah, was she? Was Deb interested in this?
Yeah.
The thing that I find, well, before I say this, the meme here has honestly been the fact that OpenAI created this eval set, but the irony is that actually, to their credit, they were very candid about this. Claude actually does better than their best model on this eval set. So it's funny, right? Because their goal here was probably to show, hey, look at how good our model is compared to other models. Our model can actually do tasks in the real world that people get benefit from, unlike maybe some of these other models. Only to come to find out that actually turns out that Claude, their competitor, does better than them. So that must have been a little bit of a tough sell for for them
For
to
their
publish
PR team.
candidly for their PR
Yeah.
team. Yeah, but good on them that they were candid about this at least. Yeah, answering your question. So if I had to think about how eval sets have been structured historically, I think the arc of how this has progressed has been that initially back in like 2016, 2018, people were trying to figure out how do we actually evaluate language models, period. Like, how do you figure out if a language model is good at language modeling? And it wasn't easy to do back then because language models just weren't very good. Like, they couldn't actually produce good text. So people had to be a little creative and figure out, okay, even though this thing can't produce text well, can we figure out, given model A that's not good at producing text and model B that's also not good, which one is a little bit better? So we had to be very generous in how we evaluate these models. And so we came up with tasks like, for instance, let me feed this review into both of the models and let's see if they can classify whether it's positive or negative. Like, honestly, the easiest task in the world, right? This task is
It's
like,
so funny in
hey,
hindsight. Yeah.
yeah, this task was like, hey, I hated this movie. It was so super bad. And you would give it to two language models, and then you would hope that they would both classify it as negative. And if one of
And
them
they'd really have to think about it. They'd be
and they'd
like,
have
"Oh
to
my
struggle.
god, I don't know,
Exactly.
dude."
Exactly. And I remember there was all these papers that were trying to figure out how do you deal with like negations when, when you have a review like it wasn't that bad, honestly. It was not the worst thing I've ever seen. Like those kind of things would be hard for language models to deal with just because there's like this double negative and there's a little bit of a subtle implication that is expressed by these kinds of reviews. So anyway, this was how we used to evaluate language models. We would find a task that was relatively simple and then just evaluate models. Back in 2018, this thing known as Glue came out, which was basically this collection of different tasks of this sort. So it was like question answering, this like review analysis task, a couple others. It was like 8 or 10 in total. And we would evaluate language models on this set of 10 tasks, this collection of tasks. And then once Transformers came out and BERT came out, all of these tasks basically got obliterated because these models were doing super well on all of them. Like they were scoring 100%. And so, as you alluded to, the fact like once a language model is scoring perfectly on a task, that task by definition becomes pointless because what's the point of reporting the metric on that task if you're just like getting it correct? So at that point, researchers were trying to figure out, well, how can we produce tasks that are trickier or that models would explicitly have a hard time solving that humans wouldn't have a hard time solving. And so there was a whole set of tasks that came out in 2020, 2021, 2022, for instance, like HelloSwag, that we're trying to figure out, can we devise tasks that are easy for humans but hard for models? And so for this, we would actually create models that would predict when a model would have a hard time solving a task. This is kind of like a meta task where you would have a model itself create a task. This process typically was trained in like in an adversarial manner where you would have models kind of like competing and trying to trick each other into producing tasks and then solving tasks. And by this adversarial process, what would result at the end is tasks that were really hard for models to solve. And so there's been basically a bunch of tasks like in 2022, 2023 of this sort. But then as models kept getting better and better, like once we got to, the GPT-4 suite, GPT-5 suite, the new Claudes, even those tasks became relatively trivial for models. And now in 2025, the tasks that we evaluate models on are ironically not generated by models themselves anymore, but we've gone back to humans generating really hard tasks for models. But now, unlike in 2018, when the task that humans came up with was, is this review positive or negative? The tasks that we're having humans create are genuinely also really hard for humans to solve themselves too. We're asking college professors to come up with the hardest, math problems or physics problems that they give their students, and we're giving those to models to solve. And in this case, OpenAI is trying to say, can we create tasks that are actually not just hard to solve, but also from an economic perspective, interesting to solve? So can we have models that could actually potentially replace junior or mid-level employees at architectural firms or accounting firms? And I think that that's pretty interesting that, we've kind of like come full circle where initially tasks were created by humans, then machines created tasks for machines, but now humans again are creating tasks for machines, for language models. I think there's some sort
Totally.
of like nice harmony there.
Yeah, we've fully gone full circle. Except now what we're benchmarking are, as you were saying, is way more practical than
Yeah.
is this sentiment review. The irony, of course, is sentiment review or some elements of summarization. Those are actually very useful primitives for a lot of business functions, like where you deploy the first deployments that we would see of these models. We're usually more in those domains or like with those task definitions than this inherent complexity that we feel comfortable to give to agents now. But as the sophistication has increased, this specific data set that I thought was pretty interesting includes multimedia inputs as part of the task definition too. The human experts themselves, as far as I can see, were given no limits as to what they would include as these references. So they would include Excel files and PowerPoints and code repos, PNGs with annotated labels, and use that implicitly to then give to the model and test the model's ability to reason about these multimedia inputs. and then output in some format that the human experts also wanted. So if you asked GPT-5 or Claude, hey, I'm working on this presentation for work, here's some input data, generate me an aesthetic keynote of the output, then part of the output evaluation would be, did this output as a keynote and was it aesthetic? So it's starting to get us into these very fuzzy territories where you're really trying to quantify, this is how these models are going to do. And I'll
Yeah.
also add that I think that whole process feels very much like it's going to lead to RL environments that are calibrated for these tasks. Because as part of this data set, they had the experts curate a matrix, like an evaluation rubric of what they were looking for in the results that the models were going to give them. And I was thinking to myself as I was reading this, oh, that actually feels very much like the components of an RL reward function for a model that's given an environment where it has access to PowerPoint, maybe with a computer use model attachment, or like it has access to a code interpreter. And then the RL, maybe some meta model, maybe actually the one that they trained here to try to evaluate these tasks is going to act as the reward function, which pushes the model to do better in these domains.
That's so cheeky. Yeah, I could totally see that. No, I mean, I think you're right. I think we are working towards a future where everything is basically RL. And the challenge is going to be to build a good simulator to train these RL agents in. But you could see there being a simulator in the future, which is like a real world work with me simulator, where it's a simulator where you're basically working with a LM and its simulated environment is just the workplace. And basically it's trying to solve these tasks and it has some RL policy that it's trying to learn as it's working with you. Something like that is definitely in the near future. I wouldn't be surprised if OpenAI is secretly working on this already. Yeah, fascinating. Absolutely fascinating.
I'm thinking of the extremes of those little robots that would wheel around. I feel like there was a demo shop in Palo Alto in 2016 of these conference robots where you could control them from afar, and then it would just be your face zoomed in on the robot. If you just put, a GPT-5,
Oh yeah, I remember this.
GPT-5 as the head instead of as a person, just meet your new coworker.
I mean, I think what we're testing our models for when we release these sorts of benchmarks is how good are they dealing with the messiness of a real workplace. And what I mean by that is when I'm working with a colleague, I expect them to be able to take my scribbles, my notes, and my like bad JPEGs or PNGs that I generate and do something with that, right?
Yeah.
That I can communicate with them. If I'm like, hey, Piers, here's a really bad mock-up of a website that I drew up. And by the way, here's like a voice note that I recorded on the go explaining to you what I want. I do still expect you to be able to do something with that information and not just say, I have no idea what you're talking about.
Yeah.
And that's something that humans are good at. We're really good at dealing with noise and messiness and like basically doing the process of inferring what someone might want from really bad, noisy inputs. Models, I think, struggle with that. And I think that that's what they're testing here. And I'll go so far as to say, I think the reason that Claude actually was better than GPT at this benchmark is because Claude is actually really good at dealing with noisy data. The reason that people think of Claude as having a better vibe is because it is able to produce outputs in multimedia that we find more stylistically interesting or that are more akin to how humans would produce themselves like a PowerPoint or a JPEG. And I wouldn't be surprised that that is the reason that human experts rated the outputs of Claude as a little bit higher than those of GPT.
Yeah, it has some like emergent property of aesthetic sense.
It just
Almost.
looks better. Like even if the content isn't better, I think Claude just tends to produce things that just look a little bit more. They have a certain like je ne sais quoi about them, where it just looks like something I would rather share with someone rather than GPT. Like GPT does still look a little bit more AI-y than Claude does, if that makes sense.
Yeah. And I mean, in the blind evaluation that they gave to the human experts, they didn't know which ones were models and which ones were people, which I think is important too. So it's like the benchmark that they had, you're just given a swath of different deliverables from like 10 hypothetical employees that you have had. And if you're really trying to say which ones are better, for the ones that are in richer fields, PowerPoint presentations, you're not going to be exclusively thinking through the content, but it's how does this look? And if you have really good deliverable, like really good content, but it's in an absolutely horrible format. Like instead of bullet points, it's paragraphs, whatever, whatever. I think in a lot of cases, people would just find that hard to parse and say, I'm actually going to go with the one that's maybe more simple or like has less sophisticated ideas because the overall package of what I'm looking for here ends up being better. There's a lot of nuance. I didn't see them publish the rubrics that the human experts created for these different task evals, but I wouldn't be surprised if there's a decent amount of nuance to some of them of, does this strike the right balance of being
Yeah.
overly detailed versus being something that my manager could grep or I could grep pretty easily.
Let me say one more thing before I forget this, and this is probably the big TLDR. If you have one takeaway from this whole thing, it's the following. It's the fact that on some tasks, in some subdomains, Claude actually reached parity with human experts. I think that is actually, for me, the one nugget of information. We probably should have set this at the very start. But Claude on, I forget what it is, but on a broad set of tasks, it reached somewhere around 48%, preference over human experts.
Wasn't that on the whole data set? That was like
It might have been
Claude's.
on the whole. Yeah, I don't know if it was on the whole. It might have been on the whole, but the point is, on a lot of tasks, when humans saw the output of Claude and the output of a human, 48% of the time, so basically 50% of the time, they preferred Claudes over humans. So that basically means that at this point, Claude is performing as well as humans. If it's like a 50-50 preference, humans versus Claude, at that point, Claude is doing as well as humans. I mean, I think that's shocking. And just for reference, I don't have it in front of me right now, but I think that GPT was like roughly a third of the time people prefer GPT over humans. So GPT clearly still has a ways to go. Claude is basically there. 48% of the time is basically 50% of the time. I find that shocking.
Yeah, Claude benchmarked to 47.6%. This was Claude Opus 4.1. And
Okay.
then GPT-5 High benchmarked to 38.8.
Yeah. Okay.
So
that's a
definitely
big difference.
Definitely
That's
a gap
a
in
massive
there.
difference. Yeah.
Yeah, definitely a gap. They didn't seem to publish in this report, in those metrics that you're talking about, Rich, specifically what settings they assign to these different models. Because if you're calling Claude from the API, you can say, what's your capacity for thinking tokens? Like 10,000 thinking tokens or 500 thinking tokens. You can assign a temperature. You can assign like different parameters to tweak the performance of the model. I am vaguely interested, since it's definitely not apples to apples. If you say, GPT-5 High with X budget for thinking tokens versus like Claude's budget for Y thinking tokens, how they think also comes into play there. Because if you really did try to say, we're going to give each model 1,000 thinking tokens, exactly how your chain of thought thinks might actually reach you to different conclusions there. A more efficient token stream for thinking might mean that your model actually does better because it has, quote, thought for longer, unquote. So a lot of nuance in here. I'm very happy they published this benchmark.
This is GPT publishing Claude's results. Like, you would think that if at all, they would probably want to hamstring a little bit Claude.
I do get the vibe, though, that the eval team as part of OpenAI is pretty separate from the other organizations that maybe would have a more vested interest. And like this to me is some real academic honesty. It's releasing a benchmark that
I mean, Pierce, to be honest with you, academics aren't honest. That's the thing. Like, when we're writing papers, oftentimes
Rich is the most dishonest guy I know.
I mean, here's the thing. It's not even dishonesty. It's frankly, you can run an experiment 100 different times and get 100 different results that differ by a little bit. And then as an academic, you then have to make a choice. How do I report these 100 numbers? I can't just have a table with 100 numbers. Do I average them? Do I take the mean? Do I take the median? Do I maybe cherry pick the best example, but maybe the example that you would actually use in practice? Maybe I got lucky with the hyperparameters, but if I use those hyperparameters in practice, isn't that the result that I would get in actual like real life anyway? Should I just use the best performance then of my model? So there's all these different little choices that you can make, and I could see them as an eval team making choices that implicitly make OpenAI look a little bit better without really being able to say we're dishonest here, but there's little choices that you make at almost a subconscious level that influence what you report. And even after that, Claude is still doing so much better than GPT. I find that fascinating.
To me, honestly, my takeaway from that is we can certainly see that the intellectual honesty culture at OpenAI is pretty strong. And I wouldn't be surprised if internally they get the memo of, hey guys, we want to be as truthful here as we can, both for public consumption, but also honestly for ourselves, right? If we know that we're falling behind on these benchmarking scores, like that lights a pretty strong fire under the other teams to be able to break apart. Okay, well, why is Claude doing better? On
Yeah.
what real world tasks are we superior? And on what real world tasks are we inferior? And then backprop that into maybe financing for the RL team or financing for more data sets. And in my mind, it actually shows that this wild west of not really having data sets for this kind of stuff for the last while. Obviously, yes, we've had data sets as they felt like they were getting further and further behind the frontier model capabilities. I think one drawback to that, honestly, is as much for the frontier labs as for anyone else trying to evaluate these things, because you're saying, hey, we just finished a run. Let's go evaluate it, see if this is actually good enough to earmark as our next big like model bump. If you don't have good benchmarks, you might actually make the wrong call. If you have 10 candidate seeds or check marks or whatever, you yourself might actually publish the wrong version of the model because you didn't have the right benchmarks that are speaking to its capabilities in the real world. So
being dishonest could shoot you in the foot down the line. So honesty is the best policy, probably.
100%. Yeah. And I think like that's true for their external persona publications. That's true for the internal too. So I thought this benchmark was fascinating. The one other thing that I'll point people to is a benchmark of theirs called WSE Lancer, like SWE Lancer, which was taking real world Upwork software engineering tasks and seeing how frontier models are able to do against those. Turns out, spoiler alert, not that well right now, which shows the complexities in the wild of actually all the stuff you have to do to be a fully capable, fully ramped up software engineering resource, even for these freelance tasks. I thought the difference between that and SWE-bench was pretty revealing, that there's actually a lot more to software engineering than just the software engineering itself. Richard, speaking of another model where I imagine the benchmark data set is actually pretty juicy, Gemini released their first open robotics model as part of their API. So I've seen blog posts from DeepMind for the last while that have been talking about a lot of their robotics capabilities. As far as I know, this is the first one that they're actually hosting that people can ping as any other Gemini model. They're calling it Gemini Robotics-ER 1.5 and Gemini Robotics 1.5, which are actually two separate models. The ER model here seems to be more of an orchestrator model. So it is just trained on text and images. It's not trained on these actions. Like within the robotic community, people draw this line of VLMs, which are just vision language models, and VLAs, which are vision language action models. Actually, I guess it really should be VLAMs, where these are models that want to output control functions for these robotic, servo motors or other things to actually tell the robot what to do. This hybrid architecture is interesting because then if you branch them, you can calibrate them for different things. Almost like how octopi have one brain in the middle and then send out signals like subtasks to the 8 different arms. It feels like that's the setup. Why are you looking like that?
Where's this fact coming from, dude? How do you know this?
You don't know this?
No.
Oh, it's like one of the coolest thing about octopuses. Yeah, they have like sub brains in each of their tentacles, which can autonomously do tasks.
Fascinating.
It's so crazy. But okay, so maybe that's not a well-known fact.
Maybe we should just talk about this.
Turns out octopi can do this. And basically what you do is, you have this IO interface with your different brains. So it's like you have your one task coordinator, which is your central brain. And then you have these like different subtasks in the arm. So, you can tell one arm like, hey, arm, crack this mollusk. And meanwhile, you can have another arm and be like, all right, well, while that arm's busy doing with that, scratch my head, if octopi get itchy, and whatever. It kind of solves the chew gum and like walk thing in this delegated way.
I haven't figured out how to do that yet.
I know. It's an unsolved problem, actually.
Yeah,
you need 3 different brains. That's the octopus analogy, but that's kind of what these models are doing. It's like you've got one coordinator model and you're like launching these sub agents that are actually going to do what the main model instructs them to do. Richard, I'm wondering how you see this whole field of robotics evolving. It feels, at least within our conversations, they've taken a backseat to a lot of the LLM advancements. But 100%. I thought one thing that was pretty cool here is this kind of is just a language model, but it's like a language model fine-tuned for robotic calls. It might even be the base Gemini model exposed to some like additional data. What's your current pulse on how these models are operating?
Well, okay, what I'll say about robotics, knowing absolutely nothing about robotics, is that fundamentally the problem that they face is the problem of transfer learning. It's basically impossible in robotics to really do transfer learning very well. And what I mean by this is that in NLP, the reason we've been able to do so well is we've found tasks that you can train a model on for hundreds of hours, thousands of hours. And that knowledge that the model gains from training on that data transfers perfectly to being able to solve sentiment analysis, question answering, creating a coding agent, and so on and so forth. Our superpower as people who specialize in NLP is the fact that our models are really good at transfer learning. And the reason that robotics people are struggling so much, the reason that they haven't had this Transformers moment or BERT moment is that transfer learning is super hard. If you train a model in a simulator, that knowledge isn't going to transfer to the real world. It's just really hard to get this right. I mean, we've talked about this before, which is the fact that there's so much entropy in the world that learning a policy for a model to perform a given task is really, really tricky. And it's really hard for that to generalize to all of the different settings that you might expose a model to in the real world. And this could, depend on small things like the humidity of the environment where you're training your model in. If you train a model in Arizona where it's super dry, it might actually start messing up if you take it north to Toronto, or maybe it's a little more humid, right? All these tiny little things that you can't even think about end up having a massive effect on the policy of these models. As I was reading this one piece here, it seems like the big breakthrough with Gemini and what they've been able to do here in this research is that they were able to build a pretty good model that does transfer between different robots without really needing to specialize or fine tune that model for each given robot. I thought that that was pretty cool.
This is like the whole embodiment thing,
The
right?
whole embodiment thing, exactly. Do you want to say more about that? What is embodiment?
It honestly was this term that I feel like I have only heard in sci-fi up until this paper. I imagine this is a relative standard in the robotics community, but it's kind of this idea of you have that brain and you can attach that brain to different things, like the big manufacturing arm in a car manufacturer or this like humanoid robot. And the idea is you're embodying this model in physical space within one of these hardware appliances.
I mean, the whole take here is that when you're training a model on language or just knowledge broadly, it's sort of like disembodied from the real world. If a language model has a notion of a cat, right? Because it's seen this in text a bunch of times, it doesn't really understand what are the physical properties of a cat. It just knows that maybe cats are animals because it's read about this. It knows that cats occur frequently in the same sentence as dogs, right? But if you were to actually probe the internals of a model, it's not like it has this like notion of, okay, when I read the word cat and I see a cat, I know that these two things are the same thing, that they're referring to the same thing. And not just that, I also know how cats behave in the world. I know that they're somewhat related to lions in the Sahara, right? Like, I kind of understand like how they fit into this global context of animals, and I know that they're pets, and I know what a pet is. So there's all of these things that language models, when they're trained in the normal fashion, just don't have this fundamental knowledge of the world. And so this notion of embodied AI is trying to take how humans process information, knowledge, words, and encode that into a language model that has, a notion of vision as well and video and understands physics in a way and understands how things are related to each other. So I think that is fundamentally the issue that robotics have, which is the fact that not just do you have to understand concepts, but you have to put them into this global context of how humans understand these concepts. And that's really hard to do.
Yeah, it's also just speaks to the generality of their training data. I wouldn't be surprised if they have figured out a way to synthetically generate data points that seem as if they're coming from robots that are physically different in the real world, because that actually does feel like something that if you're doing in the control system, you could probably do within some simulated environment. Because I mean, like one of the reasons why in the self-driving world you need to beta test the same lidar arrays and the same GPS antennas on different physical hardware cars is because even slight minutia of how these things are positioned or mounted on a car can change how it is mapped onto the training data. So you have to get like really specific in the real world across different hardware. And I guess that's the thing in this like embodiment is when you're actually feeding things into the model, as far as I'm aware, you're basically just getting image feeds. That's like your input stream, specifically for this Gemini Robotics 1.5. You're getting these image feeds. And then this sub model, this like subbrain, has to choose, okay, given the next time step, what do I do? How much do I tweak this servo motor? How much do I like interact with these other kind of almost like tool calls as part of the model?
Yeah.
And when it's doing that, like the setting of 5 on one servo motor is going to be way too aggressive versus the setting of 5 on another servo motor that might be not nearly enough. So the ability to like almost calibrate in real time as it's getting these image feeds, I think is really interesting, where it's almost implicitly learning based on its like short-term history. Okay, what are the different values that I'm going to need to pass to this physical architecture in order to accomplish the task? But also, I think importantly, not to go too overboard. Like I wouldn't be surprised if there's like a learned latent behavior as part of these models that says, if you went from 0 to 50, that'd be really bad because you could potentially overshoot what you're trying to do and whack something off the table. So it's actually much better when you're first starting off a task to slowly increment yourself from like 0 to 0.1. And then it's okay, that seems good. Okay, now 0.5. And implicitly within the history, measure how much does that actually affect the robot arm that I'm seeing. And then from there, scale it, like extrapolate that to actually what the real motor translations have to be. I think that process of what the model has learned in its RL function, not just to do the task, but like to not go too aggressively in the control system, has to be a latent part of this model and is a pretty interesting.
What you're getting at here, I think, is almost like meta learning. These models are learning how to learn. And this is a whole field of ML research outside of reinforcement learning. The irony, or not the irony, but the interesting thing is that maybe it is a little ironic actually, is the fact that robotics, even though it's often thought of as a field that has had less progress than other fields of ML or AI, it's actually the field that's led some of the big breakthroughs in things like reinforcement learning and meta learning. Meta learning, this whole field of study of how do you get a model to introspect and learn how to learn, came out of robotics and has actually found more success in NLP and in vision than in robotics itself. But roboticists, they're like trying to figure out how to make this thing work. They're trying all these different things, publishing all this interesting research. None of it seems to have really worked fundamentally, but they're doing a bunch of good work. And I think it's, eventually they're going to get a big success. Maybe it's a combination of these different things, right? Maybe it's a combination of a bunch of pre-training data using a transformer architecture with reinforcement learning and meta learning that's going to crack the code and make these models actually work well. But until then, I mean, they keep publishing really good work. So I'm really happy with what they're doing, even though they haven't found, their big moment yet.
Yeah. I mean, it might be one of those domains that actually has no big moment, but we look back in 15 years and we say, wow, they actually cracked the code via slow, very incremental progress, even if they didn't have a GPT moment or an AlphaFold moment. Speaking of AlphaFold, Richard, Apple released a model and a paper to go alongside it this past week. It's called SimpleFold, and it's their take on a generative model which is able to approximate protein folding. So our listeners might be aware of AlphaFold. I feel like that's definitely the most popular within these architectures. It was the one I think won the Nobel Prize or maybe won one of these other scientific breakthrough awards for effectively solving what was long thought of as an impossible problem, which is how do you take the DNA, almost these definition pairs, and then translate them into the physical space. If you have amino acids that are the things that compose proteins, the way that they actually fold, given they're flat, via electron attraction and relationships is very non-trivial and has been computationally pretty intractable to do in closed form. So we know that in practice, okay, we assemble this arbitrary pair of base pairs together. They might be 30 long, they might be 150 long. We know that they're going to fold in a consistent way. That's
like origami almost, right? It's like you take a piece of paper and you can fold it in all these different interesting ways. It's almost
exactly
like figuring out how you can manipulate these different things to create these interesting shapes?
There's only one way that proteins, when they fold, are, you know, molecularly stable. And
Yeah.
that stableness is driven by their electron attractions. I think they're trying to, yeah, minimize the overall energy within this overall system. So they're following physical properties, but actually having to simulate those because you have one electron interacting with hundreds or thousands of other electrons, exactly how each of those feed off of each other in real time ends up being very hard to do, again, in this computational lens. So there have been a long series of research pursuits, papers, and breakthroughs in this field because the real world implications of being able to know how proteins fold is incredibly important. It's basically like the core of all computational drug discovery is, can we figure out how to manufacture a protein that does a specific thing, but before we can know how to manufacture it, we have to know what the protein is in the first place.
Well, it's like
So
it's also like the shape of these proteins dictates their function in some way that I don't understand because I'm not a biologist. My understanding of it is like the way that something folds, that structure has some sort of an actual property itself as an entire protein. And so if you can get something to fold in just the right way, then because it has the shape, it can interact with other proteins in this way. And that might have some big implications for the types of drugs that you can use that could attack viruses in just the right way.
proteins are the ultimate, like, form dictates function. It's actually exclusively what's important to them is their form. I think we should really have a biologist on the show at some point because neither Richard or I are biologists. I can't even cosplay as a particularly good one. But anyway, the
You're
ML of it
killing it,
all.
dude. This
Oh,
sounds great.
I don't know about that, but there's certainly been this like really long history of people trying to build models that do this thing. You have this big breakthrough with AlphaFold, and to a lot of the biologists that I do know, they basically said they kind of solved it. This went from this very open problem in computational biology to like, oh, great, like this is a new primitive that we have and we can rely on. I was intrigued to see this simple fold come out. One, because it's Apple publishing this publication, which is just outside of their historical expertise or like what these labs typically
Yeah,
publish.
what are
It's like
they
a lot
up
of
to? What do they
computer
need this
vision. Maybe
model
it's
for?
eye protein dropping later
Huh.
this year. So they released this paper and it has a pretty interesting architecture, some like different training methodology. And I thought it was just an interesting thing to maybe talk about. I didn't see it get that much play online. Can you talk a little bit, maybe at a high level, Richard, about what makes this paper unique from what AlphaFold is doing, or like what problems did they set out to accomplish that weren't already in the prior art of the previous 1,000 papers that have been published on the same subject?
Yeah, sure, dude. I mean, as said, my happy space is like NLP, but I'm happy to talk about robotics and
Well,
AlphaFold.
I guess
No,
this is a little like NLP in that,
it is a
like,
little bit. Yeah.
base
Yeah, let
pairs,
me
text. It's
a little
different.
bit. A little bit. Yeah. So here's the interesting thing about this paper. If I had to summarize it, it's the following. Two things. First thing, they were able to take AlphaFold, this existing LLM, basically, this large model, and synthetically generate a bunch of data, something like 9 million data points that they were able to train on synthetically. So that's cool. So now you can basically take this big model that's, as you said, basically solve the problem of folding and generate a bunch of data that you can then use to train smaller models on. The second thing that was interesting about the simple fold model is that it uses a new technique in this space of biotech, bio AI that is akin to diffusion models in text, but applied to protein folding. And in particular, what they do is they have this notion of normalizing flow models that they apply to the problem of protein folding. Okay, so what is a normalizing flow model? So, for all intents and purposes, you can think about a normalizing flow model as basically a diffusion process. So, what a normalizing flow model does is it basically says there is some distribution out there for how points in a space interact with each other. We don't know what that distribution is. But what we can try to do is we can try to see, can we train a model that measures at time step t how each of these points in some point space are going to move in the next millisecond or nanosecond. And let's learn a model that can predict basically how things move. Like they would say that this is like a velocity model of these points. And in practice, what this might start smelling like to you is basically a model that is solving a series of ordinary differential equations. That's basically what a normalizing flow model is doing. It's solving
Definitely
basically
smelling like that to me.
smelling like that, huh? It's in the air.
It's
So
smelling
it's
sulfuric, but it's smelling.
yeah, I mean, I feel like ordinary differential equations does not smell like an apple pie. I mean, I feel like it's
You can
it's
leave it at
definitely
that.
a little toxic. So what yeah, so basically what this model is trying to do is it's trying to say, okay, if we were to throw a bunch of points in a space, let's learn a model such that it can predict how these points want to move to consolidate into something that over multiple steps will form something that could be a protein. That's what a normalizing flow model is doing when applied to this context. And so you can tell that this is somewhat akin to a diffusion model for text, where a diffusion model is basically trying to learn how do you denoise a noisy distribution to produce something that looks like text or looks like an image. This is saying if we start with a bunch of points in space, and here points could be amino acids or they could just be ambiguous points, but how do we get these things to form some sort of a distribution that we want to have? And in this case, that distribution, that form that we want it to have, is the form of how a protein folds. The innovation here is that you can apply this technique to treat molecules as these little points and learn a function for how things want to basically group together over time to form something that is stable, like a stable structure, which, when interpreted in this context, is the structure of a protein. So I thought that that was actually really cool.
Is it almost fair that this function that they're learning is almost like a general purpose electron attraction model?
I think so.
Like they're kind of like
Yeah.
learning the underlying physics implicit in how these fold by virtue of these points representing these things.
Yeah, I think what they're basically saying is that by the laws of nature, when you have two atoms in some space, there is going to be a way for you to model how they're going to move in the next time increment. So either they're going to attract each other or they're going to repel each other. And we can learn a model for basically how physics at the level of atoms interact with each other. What's so fascinating is that AlphaFold doesn't use this sort of approach. Instead, what AlphaFold had to do was they had to encode into the actual architecture some of the laws governing how different atoms want to combine and consolidate. So implicit in the actual architecture of AlphaFold are rules for these things are allowed to combine, these things are not allowed to combine, these things repel each other, these things attract each other. This model doesn't actually have to codify that into the model. Rather, it's just a learned emergent process, right? It's something that comes out of the learning itself. And that's really cool. The fact that you can learn these laws of physics and nature implicitly.
Which I think maybe speaks to why this is published from Apple versus from DeepMind is, dare I say, Apple itself does not staff a big team of biologists that are working on this fundamental research. They do, however, have a large and I think quite talented team of ML researchers. And from that POV, if they're using data that was generated from some of these much larger, much more, I don't really want to say rule based, but there's certainly a lot more heuristics. Like there's a lot more heuristics in AlphaFold than in this kind of end-to-end architecture. It's kind of showing off Apple's distillation prowess of saying, we really want these things to be able to run on the edge because, that's in Apple's interest. That's what they invest a lot of money in. Their chips are quite good at running ML models at the edge. And the specific weights or parameters that they publish as part of this, there were a few, but it topped off in this 3 billion parameter bucket. So I almost wonder if this is acting as this POC for being able to say, we can do AlphaFold on just general regular purpose consumer hardware. And we can do that via this end-to-end distilled model because once we have these things that have maybe been generated by a much more data intensive or labor intensive way with a bunch of heuristics, once we have the data, we can forget about how we got the data and just focus on now we can train a really sophisticated model that can treat that generated data as ground truth and then do something interesting and pretty efficient with the architecture selection.
Yeah, 100%. And as said, I think that Apple has, for the last maybe 3-4 years, really tried to establish themselves as a leader in the research space for small language models and small models more broadly, specifically. They've been doing a lot of really good work that I think has flown under the radar because they're purposefully not specializing in LLMs. Rather, what they're doing is they're coming up with all these really cool papers that talk about how can we get small language models to perform as well as large models, or how can we analyze small models? And it's really cool. I mean, it's like really interesting foundational work. I wonder if it'll eventually pay out dividends in ways that we don't understand yet. You know, like this paper here. Are they trying to scheme on some sort of a model that can create better protein so that they can create new materials or something like this? What is the goal here? I think it's unclear. But maybe the goal is just to say, look, we're just like going to really try to understand small models and we're going to perfect techniques for distillation, pruning, different pre-training paradigms. And that maybe will pay dividends in just, our ability to have good language models that work well on small devices or that work well on resource constrained environments. Maybe that's the play. I'm not sure though.
100%. Well, hey, maybe it's just research for the sake of research, which I'm also totally a fan of.
I love
that pushes the industry forward, even if we don't necessarily know how yet.
We love research.
What we really love is a baked apple pie.
That's right.
So I'm glad we got to cover this Apple model as well.
Incredible, dude. Every time we cover Apple, we'll have to start with an intro that relates to apples in some way from now on.
I think maybe just every time we cover Apple, you're going to have to start baking an apple pie.
An apple pie. Maybe
really
you're
get those 10,000 hours going.
I'm not opposed, dude. I feel like we made a pretty good apple pie. I'm not going to lie. I'm pretty stoked to dig into it after we're done recording.
Well, in that case, I won't hold you much longer. I'll let you jump to it.
Sounds good, boss.
Thanks, man.
All right, buddy. Pleasure.
Good
Talk to you soon. Bye.
Thursday.